In this video, we're going to be discussing high-level design and low-level design. Just as constructing a building or a road requires both the architect's vision and the engineer's specification, similarly, software systems benefit from operating at multiple levels. And this operation requires operating at both multiple levels simultaneously. Now, what is a high level design and what's a low level design? Now, I want you to understand that these two, they are not in competition. They simply complement one another. So what is a high level design? High level design simply shows the major building blocks, that is the services, the data storage, external integrations, and how data flows between these different systems, right? Or these different separate entities. So the high level design simply communicates the system overview, right, to all the stakeholders. So any stakeholder, whether a business stakeholder, your financial, your technical, whatever type of stakeholder, it simply just communicates that system overview, and it ensures everyone has that fundamental structure or have that fundamental understanding of the structure. So this is where you simply validate that you are simply trying building the right system. However, this is very different from the low level design, even though they complement one another, because the low level design is in depth, right? It is a component design which includes things like your class diagram, right? Algorithms, API endpoints, schema details. And I'll explain each of these because this low level design, it serves as the implementation blueprint, right? For your developers to follow to build the system. So when we talk about low level design, you're simply talking about your stakeholder as the developer, because that's basically how they are going to be building each part of the system. And it goes to the nitty-gritties of like the class diagram. So you see things like the information like the parent class, the children class. And if you're familiar with objective-oriented programming languages, OOP, you would find that things around class diagrams are very important. For example, in your Java, your C Sharp, things like that are very, very important. Now, back to low-level designs, it simply ensures that you build the right system. That is, you are translating the architectural vision into a concrete code, right? And like I said, the relationship between the high level design and the low level design is basically perspectives, right? They complement one another, they don't compete with one another. So every design or architecture starts with the high level design. And this is to ensure that your architecture meets your requirements and it makes strategic sense. If you go back to our previous videos where we talk about the framework, that is the DASA framework for system design, the first part, and the D stands for defining the requirements, right? So we make sure that the high level design meets the system requirements and it makes strategic sense. That is, it aligns to the business objectives. And then we dive into the low level designs to nail down the implementation specifics, right? And when you think about the high level design as your architecture or the building layout, you would look at the low level design as the detailed engineering drawings that displays the detailed vital roles that your entire design is going to be working based off of. So to simply put, right, your low level design complements your high level design. Your low level design simply just shows the nitty gritties of each of these steps. Now, whilst all of this is important, right, it is very important that we talk about the different trade-offs and design decisions that need to be made. Now, when you're navigating your competing priorities, it is super important that you are able to look at the different trade-offs. And I'm going to speak about this using four key areas. Number one is the trade-off, right? Now, when we talk about cap trade-off, we're discussing consistency and availability. We discuss performance versus cost. We discuss simplicity versus flexibility. And lastly, we'll discuss speed versus scalability. Now, system design is fundamentally about making informed trade-offs. Whether you're making a trade-off for cost or you're making a trade-off based off of your team's knowledge, right? Some teams might have more Java experts, or you might have more JavaScript experts, and you're just making decisions based off of the individual skills that you have on the team. You would have trade-offs. And when it comes to system design, we must be able to nail down what those trade-offs are from the start, because there is no perfect solution that maximizes every dimension, right? Of the length and breadth of what you're trying to do. So attempting to achieve everything simultaneously simply results to you not achieving anything at the end of the day. So I always say that the best architects understand the reality of making trade-offs, and they make deliberate choices based off of the context and based off of the priorities of the business. So let's talk about cap trade-offs, right? In distributed systems, you cannot simultaneously guarantee consistency and availability under things like network partitions. Say, for example, in a banking environment would favor accuracy over a social media tool that would favor availability. Give an example: your X, which is Twitter at the moment, you you would probably agree with me that it is important for you to be able to refresh your timeline every 2 minutes, which is essentially availability, as opposed to being able to see accurate follow accounts. Whilst in the banking sector, you look at the banking sector, the most important thing for every customer is to make sure that their account balance is as accurate at every given time. a, a customer might not necessarily complain so heavily on the service not working in that moment, as opposed to seeing probably $1 is missing from their account. So when we talk about consistency versus availability, you're looking at each of these different use cases: banking, social media, and you're looking at what in this scenario, what's more important? And that's how trade-offs work, right? And when we talk about trade-offs in this sense, we're not saying just essentially just do away with availability. What it means is you kind of prioritize even more consistency over availability in certain situations. For a case in point, banking. Now, the next point I want to make is performance versus cost. Now, you want to ensure in this case that you have or you're improving performance, and that improvement in your performance can be justified based off of its cost. So, for example, you want to be you want to be able to give high availability, right? Now, what does high availability bring in terms of turnover for the business at the end of the day, right? Because you are essentially paying for all of these expensive soft servers, hardware, and you want to be able to justify that this performance that you're buying all of this hardware and servers for can be justified. The cost can be justified, right? So you're optimizing within the budget constraints that you have rather than at any cost that it will come to you. So essentially, in this case, I would say sometimes good enough performance is just the right choice and not ultra performance, right? Um, the next point I want to make here is something I call simplicity versus flexibility. In this case, I'm going to use the concept of a monolithic architecture versus microservices. Now, monolithic architectures are faster to develop. right? For small teams, whilst complex microservices are, would I say, they offer more flexibility and more scalability at the expense of operational overhead. Now, when you want to choose for faster development, or you want to choose for availability or scalability, each of these components come into play, right? So if you want to choose complexity only when the benefits outweigh the cost. I give an example. If you're trying to build a simple website and this website is only meant to show information, you would use a monolith. You just build everything into one. And I explained in another video what a monolithic architecture is, right? To give context. Now, with microservices, it means you are sort of creating smaller units of services that basically come together to make up what a web application, a mobile application, or any type of application you're trying to have, which essentially means more cost because you're managing different services, right? That bring all together to one value proposition. And so when we talk about simplicity versus flexibility, these two examples sort of explain what we're trying to do here. Finally, when we talk about speed versus scalability, when you want to build quickly, monolith is always the best choice, right? You want to build quickly, you want to push out quickly, monolith is the best choice. But then when it comes to scalability, that is, you have more customers, more people are buying from you. For you to scale, for you to be able to manage your services, for you to improve availability, for you to basically be able to auto scale, vertically scale up and horizontally scale out, it is very important that you move to microservices. Now, it's not so important to move all your services or all the different features on your monolith to microservices. However, it's a gradual process. So, case in point, when you want to start, you look at the services that your customers leverage the most, and you start to create them as microservices. That way, you're maximizing your revenue for what's most important at any given time. And that's how I think small scale ups or startups should always leverage technology. Now, there are common pitfalls and there are anti-patterns that we sort of make across the way. Some of them include skipping requirements, not planning for failure, over engineering, trying to reinvent the wheel, and there not being a scaling part. And I think that when you learn from other people's mistakes, it's easier for you to sort of make less mistakes of your own. And so try not to skip requirements when you want to go through the engineering process or system design process. You must be able to plan for failure, right? Whatever type of failure, whether that is disaster recovery, server crashing, network partitions, or your database filling up, you need to prepare for that. Over engineering, you need to stop adding unnecessary things like a just in case that is just simply your waste your time or your resources. And don't try to reinvent the wheel. There are already processes in place. There are already systems that you can leverage using APIs. So don't try to reinvent the wheel. What's your core business model? Try to fixate on that and do that. And you must always create a scaling part. When there is no scaling part, then it's impossible to sort of build a system that is going to scale on the path of what it needs to be. I've seen systems over time whereby they need to rebuild that system because they never planned for scale, right? So if you want more information on system design, stick to this playlist. Check out the videos on here. We'll be discussing so many things around system design. And this is how I'm going to keep breaking things down little by little using simple language for all the different types of users. This is system design for beginners and only beginners because we want to make sure that this information is here and there for everyone.